All right, really quick here, just a quick review of the momentum stuff. I'm going to start back kind of in the beginning, talk about impulse, momentum, and then the collisions, all right? So when we first started this unit, we defined momentum really by its change. We started with Newton's second law, and we turned it into force times time equals m delta v. Okay? Now, this side of the equation is technically called impulse. This side is called change of momentum. Right? Now, sometimes we're literally just giving the force in time and asked to find the change in, typically the change in velocity, right? So, just a quick example of that. Let's say we have a 5 Newton force acting for 3.0 seconds on a, I don't know, 1.5 kilogram object. And let's say the initial velocity, let's make this force positive, 5 newtons. Let's say the initial velocity is, I don't know, negative 10 meters per second. So we have a force moving to the object moving to the left, negative 10 meters per second. It's got a mass of 1.5 kilograms. The force acting on it is going to be that way, so I'll draw the force vector a little bit different. The force will be that way for 3 seconds. So we say, okay, force times time equals m delta v. I'm going to solve for the change in velocity and then add that change to the initial velocity. Alright, so 5 newtons, and it's positive. We should include the sign because impulse and change of momentum are vector quantities. Time is 3.0 seconds times 1.5 kilograms times delta v. So 5 times 3 is 15, positive 15 newton seconds. Alright, divided each side by 1.5 kilograms. Oh, and look at this. Delta v is 15 divided by 1.5 is positive 10 meters per second. Not meters per second squared. Alright, so that means Vf must be 0. Alright, because your initial velocity was negative 10, your velocity's got changed by positive 10, so this force would actually stop this ball. It would actually take away all its momentum. Didn't mean for that to happen, but just kind of interesting that the numbers I picked out caused that to happen. Now, the other way you can determine the change in momentum of objects is if you have sometimes you're given a graph. So we had these ones where you said, okay, force in time, all right, let's say 1 second, 2 seconds, 3 seconds. Let's say it looks like this. Let's say that's 1.0 newtons of force. All right, so we might say in a collision, the following force versus time graph is produced. Let's say our object is moving to the right. Let's say its mass is 0.50 kilograms. Let's say its initial velocity is, I don't know, positive 3.0 meters per second. Let's say in a head-on collision, this is the force that's applied. This is the force that's applied to it over time. All right, so it's going, it hits something, has this force applied to it. So it's a head-on collision. All right, so impulse in this case is the area under the graph. So the change in momentum, or the impulse, is the area under the graph. So if we do that calculation, the change in momentum, or the impulse, is going to be 1/2 of the base here, which is actually only 2 seconds. The base of this is however wide the base of this triangle, so it's 2 seconds, times the height, which is 1 newton. 1/2 2, you get a change in momentum of 1 newton second. Now, if this ball is heading in the positive direction, it has a head-on collision, that means the force, right? The force that's acting on this object would have to be to the left if it's a head-on collision. Right? So that means the impulse is negative. The force is negative. Therefore, the impulse, which has a symbol of capital J that I don't like using, so I'll just write impulse, is also negative. When you're given these graphs, we're typically just given positive values. Well, that's the force that's applied to each object when they collide. So, to the object initially traveling to the right, the force would be to the left. To the object initially traveling to the left, when they hit, the force would be to the right. So, the way I drew this for this object, the force has to be to the left, so the impulse has actually got to be negative for this one. All right? So now we say, okay, impulse, force times time, right, which is the area under the curve in this case, negative 1 Newton second equals m delta v. So negative 1 Newton seconds equals 0.50 kilograms times change in velocity by both sides by 0.50. Kilograms cancel. You get a delta v of negative 2 meters per second. So if it was traveling at positive 3 and it changes by negative 2, that means v final would be positive 1 meter per second. So in this head-on collision, right, the incoming object would slow down, and the object initially moving in the positive direction would slow down. This one would probably have to bounce backwards or either stick to it and move along with it. That would depend. So that's impulse. Now collisions, I'm going to go over the second question on the quiz. First question was a good one. You can send that, we did this one in class, but I think one of the previous videos goes over this one. In fact, this one here, I think one of the previous video goes over as well, but I'll just put it in with this one. So in any collision, momentum must be conserved. So P before always must equal the momentum after the collision. All right. So in the quiz, I had you draw a before and after diagram. So we had a 0.255 kilogram pool ball moving at positive 6.0 meters per second. We have a stationary rubber ball to make it look a little different. Its mass is 0.170 kilograms, and its initial velocity is 0. All right. After the collision, the pool ball slows down. Its v after the collision is positive 2.0 meters per second. Its mass is still 0.255 kilograms. And the rubber ball bounces off. Its mass is still 1.70 kilograms, but we don't know its velocity. All right? So P before equals P after. So the total momentum before the collision must equal the total momentum after the collision. So 0.255 kilograms. I just start doing all the little MVs of each object before and after. So this one's mass times its velocity, positive 6.0 meters per second. This one's mass times velocity is 0 because its initial velocity is 0. That's got to equal this one's final momentum, its mv, plus this one's mv, must add up to equal the single one's mv afterwards. So this one loses a lot of velocity. This one's obviously going to gain velocity. So 0.255 kilograms times positive 2.0 meters per second equals 0.170 kilograms times the unknown velocity v. Now there's lots of different ways to do this. You can multiply these two together, multiply these two together. You bring this one over here if you want to do it all at once. So 0.255. I stop writing the units once I've substituted in. Minus 0.255 times plus 2.0. Because I've done everything in kilograms and meters per second, so I know my answer is going to come out to be meters per second. I'm not going to continue on with the units here. Equals 0.170 Now there I go putting the units in. 0.170 times V, divide both sides with 0.170. Alright, V comes out being 6.0 meters per second. And the answer does come out positive. So that means this one bounces to the backwards to the right at positive 6 meters per second. Now the last one I want to remind you of is something like we did in class on one of the problems. This one, something explodes apart. So I said, okay, I did a little example today in class where it was like a spring toy. So let's talk about the carts, right? Let's say I have two carts, all right? They're stuck together. There's a spring between them, all right? All right. Everything's initially at rest. Let's say one of them's got a bunch of mass on it. So this one's mass is 0.50 kilograms. This one's mass is 1.5 kilograms. All right? So that's before the collision. We pushed a little spring that's between them, and they blast off of each other. All right? This one is observed moving to the left. Let's say at 1.5 meters. Oh, no, I shouldn't do that. I'll do 2.5 meters per second to the left. And since it's to the left, it would have to be negative. We want to figure out with what speed is that one going to bounce backwards. Now, somebody in class immediately knew the answer, and they, knew it right away. So it's kind of that was kind of cool. Just by the simple proportion, because P before here has to equal P after, and P before its total is 0, right, initially. So that means these two MVs, they must be equal. So 0.5 times 2.5 has to be equal to 1.5 times whatever its velocity is. So it's got to be something less than 2.5 because its mass is 3 times bigger. It actually should be 3 times smaller. The velocity of this one will have to be 3 times smaller than this one. But let's show that out. So 0.50 kilograms times the velocity, negative 2.5. You absolutely need the sign in there to get this to work out algebraically. Times V. All right, so 0.5 times 2.5. Well, that's like 1.25, half of 2.5. And it's negative, so I'm going to bring it over here, so it's going to end up positive 1.25 kilograms times meters per second equals 1.5 kilograms times V. Divide both sides by 1.5, divided by 1.5. V equals, I don't know what that is, 1.25 divided by 1.5. I don't have a calculator anywhere here handy on me. It's probably like 0.8 meters per second or so. I'll double check that in a minute. Or even a little bigger than that, maybe 0.85. We'll see. I'll double check it in a second for you. But the general procedure is what's important here. All right. So that's pretty much it for momentum, the collisions, right, and the impulse. All right. So again, let's kind of recap what we just talked about. Force times time equals m delta v. That's your impulse equals change in momentum. I usually solve for the change in velocity. Sometimes you might have to figure out the mass, right? Like I could give you the change in velocity and say, okay, what's the mass of the unknown object? Which would be the same procedure, right? You just divide both sides by delta V instead of the mass, and then you have the mass. Area under the curve equals impulse. That's a very important concept. Good stuff. Often rectangles, sometimes triangles. I wouldn't throw any weird shapes at you guys this year. Once you get the area into the curve, set that equal to m delta v, just like the previous problem. Collisions, momentum before has to equal momentum after, and it's the total momentum. So sometimes you have to keep track of the objects individually. Sometimes you have to keep track of them stuck together. All right, so that's about it for this unit. Pretty quick unit. Going pretty well here in school so far, so hopefully you guys are doing well at home. All right, talk to you later.